Very good. Okay, so what I want to start with is a discussion of quantities and units. Um, the the so quantities and units. So not everyone uses the same terminology, but this is what the textbook uses. So I'm going to use it. A quantity is a I hesitate to say parameter. It's a well, really, the way you would define it is a quantity is a useful way useful way to parameterize uh, or uh, or organize our observations of the world. Okay, so yeah, that's sort of like some sort of third grade science definition of something, but so it's just a way to organize your thoughts about the world. So as I'm looking around my living room, um, and as you guys are staring at the clock, wondering how much longer can this class go. Okay, so we're using and we're kind of organizing the inputs in different ways. Um, so examples of this might be length. So so that's, well, we know what it is, right? It measures, well, it's this quantity we associate with length. I'll talk about how we define it more precisely in a minute. Time. Can anyone think of other quantities that we use to parameterize or organize the world around us? Something else we might use.
Mass.
Mass, yeah. Okay. Um, we could have, what else could you have? You got temperature. Later on, we'll talk about energy. We'll talk about momentum. Lots of, okay, so you get the idea. These are the variables. These are the ways that we sort of organize the world around us. In particular, I'm listing things that come up in physics. There are other ways. Other things, volume, area, right? Those would be also good quantities to use to parameterize or organize our thoughts. Okay, so these are concepts, right? I haven't said how you measure length, how you actually measure it, or even if something is measurable, right? So some ways that we quantify or quantities may not be actually nicely quantifiable, um, like maybe taste. I don't know, right? That's a way we interact with the world. It's harder to quantify some things. Okay, so how do we measure and how do we? It turns out these things I've written down we do quantify. All right, how do we quantify and make a measurement of length? What do we actually do? Have you ever thought about that? Well, what we actually do is by by agreement, okay, we come up with a procedure. We agree that we will do something in a uniform, consistent way, and we define a unit based upon that process. So, um, I don't want to get into the kind of technical ways of how you do it, but basically we all agree that that a stick that can be kind of calibrated in a certain standard way, we will call that a meter, for example. Or you could do another one if we use other sets of conventions where we define something called an inch. Okay, and once you have that, then we can we can measure other things by comparing it back to our standard unit amount. So, you know, if I say a foot is this much, then I can measure other things by kind of maybe I could make a real stick that is length 1 foot, and then I basically line other objects up compared to that, and I see, oh, it takes, I can, if I do that 12 times, then I say that the car is 12 feet long, or whatever. Okay, you get the idea. That's kind of the idea how we make it. So there's a quantity, which is sort of a more abstract notion, and then we define units to quantify, to kind of make measurements of the different quantities. Okay, so units are standard or benchmark uh, um, measurements of a quantity. Sorry, I'm struggling with my trackpad here. What's the deal? Measure. Weird. Oh, now I see the deal. I ran off the edge of the page. Measurements of a quantity. Okay, so like for length, we would have meters, and let's see what else. Let's see, we would have for length we would have meters or meters or meters or no, there are other unit ways to measure it. You could also define 1 foot or 1 mile or 1 inch. Incidentally, what do we call people who use meters? Civilized. What do we call people who use these? Barbarians. Sorry. Unfortunately, though, the world is full of barbarians, at least around here. So we have to be able to talk to everybody. So, all right. But we will mostly use the metric system, and I'll talk about that. But mostly we will use the metric system. There will be some problems where you have to you have to convert between them. But okay, most things will be metric. Okay. Time, this we use seconds, time. So we'll define 1 second. I mean, these things are now defined in terms of, see, a second is defined in terms of the amount of time some atomic transition takes. And then what we actually do is we define a meter in terms of the distance light travels in a certain amount of time. So the actual way that we benchmark and standardize these things can be a little complicated. Historically, they were, a meter was like, whatever the length of some piece of metal, and a second was whatever. But now we do it according to basically we use atomic physics and quantum mechanics to kind of do that, because to the best of our abilities, we try to benchmark these things to fundamental constants of nature that we believe are unchanging, and therefore we can make things really, really precise. You always want to go with the most precise way of making a measurement to eliminate unnecessary errors. But okay, so historically they were done one way. Now they're all tied to atomic measurements. Mass. The way we measure mass is we're going to use kilogram. Is going to be our, we're going to define kilograms. You could also have pounds. Uh-oh, we already run into a problem there. There's a concept of a pound of mass, and there's a concept of a pound of force. So I will always write LBM, so we don't equivocate. So we don't use the same word pound, and it has dual meaning. They're different. A pound of mass is different than a pound of force. There's a connection between them, but they're in general different. And so I'll talk about LBM for pounds of mass, and I'll talk about LBF for pounds of force when it comes up. If you've done this in other courses, they probably didn't bother to differentiate. What's another measure of mass that barbarians might use? Do you know of any others that barbarians might use? The actual, well, have you heard of a slug? No. All right. A slug is, I always get it backwards here. Let me think about this for 1 second. I think a slug is roughly 32.2. So 1 pound divided by 32.2, I think. But anyways. So, okay. These are different. So we have units. Sorry, we have quantities. Oh, I made these too big. We have quantities, and then we measure them with different units. Okay. The fact that we have different units means that we could, and the fact that different people might choose different base units, and we're going to talk to people, whether we like them or not. So we have to talk to barbarians. So we have to be able to convert back and forth, back and forth. So that sets up the concept of a unit ratio. So to do this, let's kind of set up different ways of how this might go. Let's do length. Okay. Let's talk about let's talk about feet and inches. It's kind of simple. So 1 foot is it's an amount of length. What is that? What's the relation between 1 foot and inches? Also an amount of length. Did somebody call it out?
12
How many inches? Sorry, say it again.
12.
12. All right. Now, it's important to note, I'm not saying that 1 equals 12. The label matters. Okay. 1 inch equals 12. Sorry, 1 foot equals 12 inches. Okay. It's only true if you put the labels there. You can't say 1 equals 12. All right. I'm originally from Indiana, where they tried way back to define pi to equal 3. You can't do that, and you can't define 1 to equal 12. Sorry, just doesn't work. Okay. All right. So However, if I have whatever this is, let's just call this A, and whatever this is, and I just call it B, whoa, A, and I say A equals B, what is A divided by B? 1. Whatever it is, if they're equal and you divide them, you get 1. Pure number 1. Right? No units on this. Is everybody clear on that? So that's kind of the trick to unit conversions. And every year I get people who struggle with this. It's not hard, but it is important. Okay. So turning that around, I learned that 1 equals 1 foot divided by 12 inches. It's also true because, again, there are no units, and 1 is its own reciprocal. I can say that's 12 inches over 1 foot. Right? 1 equals 1 divided by 1. Right? So, all right. Because we've written this, and it really is just a pure number 1, and it's its own reciprocal, then you can say this. It looks weird, but it's true. All right. And that's going to be how, and we're going to use this to change units. Okay. So let's do another one. So, let me say this. This is called a unit ratio. Is a ratio of equal amounts expressed in different units, aka also known as 1. All right. So that's what a unit ratio. So this unit ratio, so every time you have an equality between two amounts, basically by dividing them, you can turn it into a unit ratio. So unit ratios would be 1 or 12 inches over 1 foot, or 1 foot over 12 inches. Okay, those are unit ratios. All right, what about time? We could say we have 1 hour equals 60 minutes. And we could say 60 minutes, sorry, 1 minute equals 60 seconds. All right. Take a second and turn each of these into unit ratios. Okay. So hopefully you can kind of follow your nose from what we did above to say so I could write this as 1 hour over 60 minutes, or 60 minutes over 1 hour. Down here I could say 1 minute over 60 seconds, or 60 seconds over 1 minute. Easy. Okay. All of these are equal to 1. I'm just writing 1 in a clever way, or well, we'll see. There are clever ways to write it, and there are not so clever ways to write it. Okay, but they're all equal to 1. They're all unit ratios. Okay, how is this useful? Well, let's see. Let's say I had 2 hours. All right, we all know that's 120 minutes. But let's use a unit ratio to convert that to minutes. How do we do that? The way you do that, so I guess I'll just call this conversions. The way you do that is by multiplying by an appropriate unit ratio. So how do you do that? Well, I'm starting with hours, and I want to end up with minutes. So I want in minutes. Okay. So what I'm going to do, I want some ratio that's going to connect hours to minutes. Well, clearly I'm not going to use these because they don't involve hours. So I want to use this one up here. And basically, you're just going to multiply, and you want to choose the one which cancels the bad stuff, quote unquote, and leaves the good stuff. So it gets rid of what you don't want and leaves behind what you do want. So I notice if I choose this one, I'm going to get hours squared divided by minutes. Okay. It's not going to do what I want. So I want to, basically I want to take this thing, I want to multiply by 1, but which I'm always allowed to do, because you're free to take anything and multiply it by 1. That does nothing. But you want to do nothing in a useful way. So you don't want to multiply it by 1 using this relationship. You want to choose this one. Okay. Okay, does everybody see? All I'm doing is multiplying by 1, just written out in a funny way. And by doing that, I see that the unit, the units here, the labels, will cancel. And I'm going to be left with 2 times 60, 120 minutes, which is the answer we all know is correct. Piece of cake. All right. What if I wanted 2 hours in seconds? Could somebody tell me how they would go about doing that?
I guess you convert it into minutes first and then to seconds.
Yeah. So what the way I would think of it as, I would say this equals 2 hours. Now you don't have to write, once we do this, you don't have to write it out. So you don't have to say multiply by 1 every time, but I want to write it like this. 2 hours equals 2 hours times 1 times 1. And then what I'm going to do is I'm going to use hours to minutes, and then I'm going to use minutes to seconds. So I'm going to say that's 2 hours times, sometimes I put parentheses around the unit ratio, so it's really obvious. And I'm going to do 60 minutes over 1 hour. And I'm going to do 1 minute is 60 seconds. Okay. This is 1, and this is 1. There are we had 4 ways to write the number 1. Of the 4, I'm choosing, you have to have a little judgment, and you have to choose the ones where it helps you achieve your goal. And you'll notice you always kind of line it up so that the stuff you don't want divides out and goes away, and I'm left behind with what I do want. And so I'm left with 2 hours, 2 times 60 times 60. So 60 times 60 is 3,600. I double it, I'm going to get 7,200 seconds. Okay. Let me pause there. I haven't done much with you guys, or really anything with you guys yet. Is this clear how I'm laying it out and doing it? Can you give me a thumbs up if you feel like you could do this piece of cake? Awesome. All right. Is this more or less how you've done unit conversions before in other classes? Some people say yes. Some people do learn to do something where they would maybe write it. I've seen people write things as like 2 hours and then like a line 60 over 1 minute, hour, line 60 seconds over 1 minute. Have people done that before, written it like that before? It doesn't matter. I mean, ultimately you're just multiplying and right, it's the same thing. So don't be confused. Don't let the notation confuse you unnecessarily. Okay, good. What about composite units? So a composite unit, so what's going to happen is we are going to have a family of kind of fundamental units, namely length. So the fundamental quantities are going to be length, time, mass. For us, that's about it. Charge is going to be the other kind of fundamental unit in nature. And we're going to define kind of building or basic fundamental units for those things. And then every other thing in nature can be expressed in terms of them. So those other more complicated quantities, we say they are composite. They're built out of the more fundamental things. So ones that are going to be, so these are built out of length, time, mass, and charge. Okay. This semester, we won't deal with charge, but that would be the other one. All right. So for example, we could talk about, let's talk about velocity. Okay. So velocity is a quantity and it has units of length. Wow, it's a quantity which goes like a length over a time. Okay, so it's composite. It's built out of more simple things. So let's just do one here. I'm just going to go ahead and give you some facts, some equivalences, and then I want you guys to do a unit conversion. I'm going to tell you that one, what do I want to give you? I'm going to give you that 1 meter equals 1.1. No. Yeah, let's do that. Yard. And I'm going to give you that is, oh, sorry. Get rid of that. I'm going to give you that 1 yard is 3 feet. Okay. So hopefully the second one, I don't know how, I don't quite know how many international students we have. So maybe international students don't know that one. Not everybody knows the first one, but anyways, these are just kind of different amounts. What I want you to do is to convert 1 meter per second and convert that to, we'll do it to 2 things. Convert that to yards, sorry, not yards, feet per second. And then just for fun, let's convert that to I don't know, feet per hour. Okay. So take a second and do that. So let's go through the process. What I would say is we've got these equivalences. You can turn those into unit ratios. And you basically have to figure out how do you multiply by 1 to go from meters per second to end up with the units you care about. Give me a thumbs up when you think you've got it. Thumbs up. Another second here. Most some people are still working. All right, I'm going to start in. If you're still working, it's okay. I'm going to start in, and if you're stuck, you can kind of follow along. And if you've got it done, you can just check how you did it, see how it compares to how I did it. So I'm going to use these relationships and the previous ones with time to construct unit ratios. And let's see. So first one I'm going to do is feet per second. And to get that one, I'm going to say, I always write down the starting point, 1 meter per second. I'm going to multiply by, let's see, the seconds are already where I want, right, in the denominator. So I don't have to do anything with those. So I just don't even worry about that. It'll just go along for the ride. Then I want to convert meters to feet. So I don't have a conversion directly going from meters to feet, but I can go meters to yards and yards to feet. So I have to do it in 2 steps. So I'll say 1.1 yard divided by 1 meter times, now I have to convert yards. So this gets rid of the meters, but now I have yards. I don't want that. I want feet. So I'm going to have 3 feet is 1 yard. And before I type it all in, I kind of do a quick inspection. I see that the meters canceled, the yards cancel, so all the stuff I don't want goes away, and I'm left with feet upstairs and seconds downstairs. If you do that, it's going to work out. Wow, I don't have to do that, right? 3 times 1.1 is 3.3. Okay. If you got that same answer, can you give me a thumbs up? Yeah. Okay. Okay. Now let's do feet per hour. I could just use this answer and go from there. I'll just start from scratch because, small town, not much to do. Let's do this. 1 meter per second. I have these same conversions here to get it into feet. So I'm going to have 1.1 yard per divided by 1 meter times 3 feet divided by 1 yard. Okay, so that's going to get me from meters to yards, yards to feet. That's good. But now I have to deal with seconds. So I have seconds downstairs, and I want to get hours downstairs. So I need to choose the unit ratio where the seconds downstairs will cancel. That means I need to do 60 seconds to 1 minute. Oh, that's not quite what I want. So now we got to get minutes to 1 hour. Cancel, cancel. Let's see. Seconds, cancel seconds. And so I notice I kind of do an inspection. I've got feet divided by hours. Now it'll work out. So, oh, somebody should have complained. I just did that. So I wrote 1/1. That was me giving you guys a chance to shine, and none of you took me up on it. Okay. I do that from time to time because I'm so generous. There's a 60. I like to give people chances to shine. So basically, I need to take 3.3 times 3,600. 3.3 times 3,600. Yeah. Okay. So I am getting 11. There you go. And the units on that would be feet per hour. Okay. Did you guys get the same answer? Yes. Okay. So notice when you have these composite units, you just string together more and more unit ratios. And that's it. Okay. Okay. Any questions on that before we move on? All right. It's the metric system. Dun, dun, dun. Okay. So wow, it's really big. It was when I wasn't full screen, it looked okay, but now I'm in full screen. Is it giant for you guys too? Like it takes a whole screen? All right. Whoa. I'm going to shrink that a little bit. And all right. Go. Fit width. There we go. Okay. So the metric system, which we will use a lot, is a system of a way of defining different units, but they're all related by simple conversion or simple factors, powers of 10. So and don't be worried, it's a whole yada fun. Oh, nobody's laughing. That's not good. Physics jokes are bad. All right, sorry, they just are. No, they just are. I can't. They just are. Sorry. So here's a list of names. You'll notice most of them, the naming here, have they differ by powers of 3, factors of 1,000. Okay, with a few exceptions. Okay, so you don't have to bother to write them all down unless you want to. I'm going to post this anyway, so it'll be there. The ones you should know, though, I will highlight because that's really important. Change color. Okay, the ones you should know. You should know. Not so much for this class, but it does. Oh, sorry. Come on. I'm supposed to draw on top of it. Why is that? There we go. Switch. Let's try that again. The ones you should know are, let's see, you should know this one this one. So you should know deci is tenth, deca is 10. You should know centa, like centimeter, is hundredth. Milla is thousandth. These bold-faced ones you should know. Yeah. Micro, nano, pico, not so much for this semester, but you should know, you'll need it. If you take physics 2, you'll need it because pico amounts of charge come up in things. Kilo, mega, and giga. I suppose now that we have bigger computers, tera comes up too. Okay, these are the ones that come up quite a bit. These other ones, I'll be honest, I guess I know peta, but I don't remember these. And I know femto because that comes up in it comes up in things in kind of atomic physics and stuff like that. But these are the ones you should know. Don't bother with the others. So the way this works is you take any basic unit, but the metric system is really, people are thinking of meters, grams, but for us, the basic unit of mass is going to be kilograms. Okay. But really that's for us. I'm trying to think. Those are the ones we're going to use. You could use this system for other things, but maybe people don't. Oh, I know in time. This comes up with computers. People talk about gigahertz, right? Giga. Right, so you're talking about billions, 10 to the 9 hertz, which is cycles per second. People talk about what about flops with computers? People talk about teraflop computers. What does that mean? Does anyone know? Flop in computers means floating point operation. So it's, again, how many, you're talking about how many processes can it do a second. Trying to think of other times. Anyways, these words come up. You should know them. Micro means millionth. Nano means billionth. Pico means trillionth. But the big ones are milla, thousandth, and centa means hundredth. So these are the ones you should know. So the way this works is we have a basic amount, like a meter. Sorry, yeah, a meter. And then from that, we can build up other amounts which are simply related to it. So by powers of 10. So for example, I can build up 1 kilometer. I'm supposed to use a lowercase k. K for kilometer. And the way you indicate that is just by putting a prefix in front of it. And it equals, so you go over to K and it's 1,000 times 1 meter. Okay, so a kilometer, the way you indicate it or label it is with a prefix way of writing it. So km is going to be 1,000 times a meter, because 1,000. You could have 1 megameter. That would equal 1,000,000 times a meter. I'm not going to write 1 anymore because I'm lazy. Okay. You could similarly do millimeters. Okay. So they're going to go around. Milli, the symbol uses lowercase m, which I used, and it's 1,000th, 10 to the negative 3 meters. Okay. So this is just a way of relating and defining different units. They all are simply related to some kind of basic building block. The reason we use the system is it gives us a way, here's what are good units? Ideally, a good unit would keep the numbers manageable. Okay, so basically manageable to a human brain. So if I'm measuring, I don't know, if I'm measuring the size of a pen, I don't want to use miles because it ends up being some tiny fraction. And basically, if you find yourself having to count how many zeros in the number, or then you're using bad units. You want to use units so that you can just say, oh, it's 12, whatever. Oh, it's 106. Those are numbers I can keep in my head. Even maybe a tenth or 100th. But if I'm having to say, oh, it's a millionth of a meter, well, I don't know. I kind of get lost in the middle of that number. So that's the idea. You want to kind of use units which make things easy to hold in your mind. All right. Questions about the metric system. I assume everyone has seen this at some point. Give me a thumbs up if you feel confident with the metric system, with doing conversions. Okay, good to know. All right, here's what we're going to do. I've been going for a long time here. You guys, let's take I don't know, let's take a 5-minute break, and we're going to come back, and you guys are going to work and kind of break out in different groups and do practice problems. All right, so take a 5-minute break, and then we'll come back.